Hello all, good morning. This is Dr. A. Arulmori from the Department of Physics, St. Joseph College of Engineering. Welcome to this session. Today we are going to see when the light and the matter interaction. So if a light is made to incident on the atoms or molecules, what are all the processes are possible, and in addition to this we are going to derive the Einstein's theory based on that. So finally we will come to derive what is Einstein's coefficients capital A and B. Okay. So now I will write the heading principle of spontaneous emission and stimulated emission. Then Einstein's theory, Einstein's quantum theory of radiation. Okay, so this is today's topic. We are going to see principle of spontaneous emission and stimulated emission, then the Einstein's quantum theory of radiation. So here I will just give when light, we all know light, which is nothing but made up of photons. So light is absorbed by atoms or molecules. It moves from ground state. The ground state can be otherwise called as excited state. Ground state, which is given as E1 to the excited state. So the excited state can be otherwise called as higher energy state. So excited state can be represented by E2. So a light, if it is absorbed by the atoms or molecules, it will move from automatically from the ground state to the excited state, because initially the atoms are all in the ground state. So we are giving the external inducement by inserting the photons. So after that the absorption, they will go to the excited state. This is our phenomenon. And here, if here we are going to consider, let us consider an atom in the ground state, E1 is triggered, or you can say by means of inducement, triggered by a photon of energy E, which is equal to h nu. See here, this energy which is equivalent to this frequency of the incident radiation, and h is nothing but the Planck's constant. So here we have before that E directly proportional to the frequency, and in order to remove the proportionality sign, the constant is being introduced. That constant is taken as h. H is the Planck's constant, nu is the frequency of the incident radiation, E is nothing but the energy. So here, if you do like that, what will happen? Three distinct processes distinct processes occurs. What are they? What are the possible three processes? First one we will see stimulated absorption. Stimulated absorption. Here you see we have added this word stimulated, which means we have to induce the atoms. Okay? So, inducing with external energy is to be given to achieve this absorption process. So, second one is nothing but our spontaneous emission, and third process is again stimulated. Here we are going to give it as this stimulated emission. So, these are all the three processes when atoms are exposed to the external radiation, which is in the kind of photons. Okay? Stimulated absorption, spontaneous emission, and the stimulated emission. Then we will see these three processes one by one. Okay? Now, I will write the heading, first heading as stimulated absorption. For stimulated absorption, we need to consider to explain this process. Here, I am just considering two energy levels, E1 and E2. Okay? So, E1 and E2. E1 is nothing but our ground state. E1 is ground state. What is E2? E2 is nothing but the excited state. Okay? Excited state. Or you can call it as the lower energy state, or you can say this as the higher energy state. Initially, I told you all the atoms are in the ground state. I am considering an atom. Okay? So, this is nothing but atom. We can give this figure caption as stimulated absorption. Here, I have to induce external triggering to be given to achieve this absorption process. For that, I am just making a photon of energy E, which is equal to h nu. Already I have mentioned here energy of photon E is equal to h nu to be incident on the atom in the ground state. So, according to this, I am just giving a photon with the energy E is equal to h nu, where this energy should be equivalent to the energy difference between these two energy levels, that can be equal to E2 minus E1. Okay? So, if this incident photon hits this atom, what will happen? Immediately the atom absorbs the energy. So, what will happen? The absorption process achieved. Okay? So, absorption occurs. So, this process by means of this external triggering, which is called as the stimulated absorption. Okay? So, for this process you need to describe this diagram. Okay? For that I can write this description in this side. Please note it down. So, first the atom in the ground state, what is given as ground state? That is E1 is given as the ground state. Okay? Atom in the ground state E1 is made to absorb a photon of energy E is equal to h nu, then it moves to the excited state, and it is represented as E2. So, this process This process is called stimulated absorption. You can highlight this stimulated absorption here. Okay. And we have given an atom, that number it should be added. So I am just writing, let N1 be the number of atoms in the ground state E1. Okay. After this description, we have to give the rate of absorption equation. So for that, I am just writing rate of absorption can be given as RAB, which is directly proportional to two phenomena here. First one is of N1. Already I have given what is N1. N1 is nothing but the number of atoms in the ground state. Okay, just I am writing as GS. I think you all understand about what is GS, ground state. Okay, for simplification I am just giving like this. So next one is this rate of absorption also directly proportional to this rho into nu. Okay, rho nu, that is nothing but the energy density. What is this energy density? It is nothing but the amount of energy incident per unit volume. Okay, we are giving this photons, no? So that one here we have represented as rho nu. So here we have the proportionality sign. All of you know about what we have to do the next step. So RAB directly proportional to N1 into this rho nu, and I have to concentrate on this proportionality sign. Therefore, AB which is equal to, or AB which is equal to, here I am introducing the constant as V12 N1 into rho nu. Okay, I am just boxing this equation and we can take this as the first equation. So the rate of absorption which is equal to this constant, then number of atoms in the ground state and the energy density. Okay, clear? Then here you can ask me, what is this 1,2 represents? 1,2 represents the transition taking place from the ground state to the excited state, or from the lower energy level to the higher energy level. Similarly, we are going to show 2,1 also, that represents the transition from the higher state to the lower energy state. Clear? Okay. Here I am just writing this because we need to give this explanation also. Already you know what is N1 and this rho nu. In addition, I am just writing what is B12. So B12 is the constant. You know, it is a constant we have introduced to remove the proportionality sign. B12 is the constant which gives the probability of stimulated absorption transition per unit time. Okay, per unit time. So now we have finished the first process. Okay, so if light, if it is incident on the atoms, we have discussed about 3 processes, and now we have finished the first one. I think all well known about this process, and you are going to make thorough with this part. Okay, so shall we move on to the next one? Okay, so spontaneous emission. Clear? Second process is spontaneous emission. So, from the name, that is spontaneous itself, you can able to understand without any external inducement or without any external triggering, the emission is going to be happen. And before that, just I want to clarify this concept. If you excite the atoms to the higher energy level, the lifetime of the atoms in the excited state is very less. So, it cannot stay in that excited state for a long time. So, it will systematically it will come back to the ground state. So, during this transition, during the downward transition, it has to emit the absorbed energy. Clear? So, under that concept, okay, during the downward transition, what will happen? There are two processes. One is spontaneous emission, another one is of stimulated emission. Okay. So, for that, just again we need to consider two energy states, E1 and E2. Now, can anyone tell me where is the atom now? Because already we have given the energy, it will stay in the excited state. Clear? So, now we have to target on the atom which is in the excited state. Clear? So, it will automatically come to the ground state. Automatically come to the ground state, and it has to emit the energy E is equal to h nu. So, here also you can write that is photon. Okay? Photon of energy is equal to h nu. So, here you can add this as excited state, and here it is nothing but the ground state. Clear? So, pictorially you should represent this. In the first process, we have mentioned what is N1. Clear? I have given this as N1 is the number of atoms in the ground state. So, in this process, you need to count the number of atoms in the excited state, because we are targeting on the excited state, isn't it? So, here N2 is the population of the excited state, or we can say the number of atoms in the excited state. So, this process is to be explained in sentence. So, for that I can use this side. Here the explanation is atom in the excited state is to be written. So, here the atom in the excited state E2 will return to the ground state, E1 without any external triggering or external inducement. Okay, so you can write like this, or without any external inducement. So, now we have explained this process. So, without any external inducement, the atom is being on to this ground state. During that emission, what else it will do? The atom in the excited state will return to the ground state without any external triggering, thereby emitting a photon of energy is equal to h nu. So, this process is known as spontaneous emission. Clear? So, you can highlight this spontaneous emission also. Okay? And in addition to this, let N1 and N2 be the number of atoms in the ground state and excited state. Okay? Excited state. Already I told you we should carry out this N2 also. Stimulated emission. Again, we have to consider the two energy states. One is of E2 and here E1. This is our excited state, and here we have the ground state. Very simple. Here I am considering an atom again. The emission is going to taking from the higher energy state to the lower energy state, and but here what is the difference? Here we are going to do means we are going to induce the atom in the excited state by hitting a photon of energy E is equal to h nu. So, this is E2 minus E1 which is equal to E which is equal to h nu. Clear? And during this or after this inducement, what will happen? The emission occurs. But what is beautiful thing here? This atom during the downward transition, it is going to emit double the amount of energy. So, here I can write E is equal to h nu, then E is equal to h nu. So, this is nothing but photons. If you see these photons are with the same energy and they are all in phase, directionality is also high. So, this is going to be a key process for the occurrence of laser beam, stimulated emission. Next, what we have to do? We have to describe this process. Third process, atom in the excited state can also be induced by excited state E2, we can write excited state E2 can also be induced by hitting a photon of energy E which is equal to h nu. So, after this hitting, what is going to happen? During the emission or during the downward transition, it emits two photons with same energy, phase difference and directionality. Okay. So, this process is called stimulated emission. Are you able to follow my handwriting? Okay. So, here this is our stimulated emission process. You can highlight this stimulated emission. What we have to do next? We have to write the equation, isn't it? Okay. So, rate of stimulated emission rate of stimulated emission can be represented as RST directly proportional to, can anyone tell me what are all the parameters we need to consider here? First one, very good. The first one, RST directly proportional to N1, and secondly, yes, secondly it is directly proportional to rho nu, energy density. So, sorry, here N2 into rho nu, that is number of atoms in the excited state, and this is nothing but rho nu, energy density. Okay, and then we have to introduce the constant RST, which is equal to, already we have used B12 for our first process, second process A21. Here also I am going to use B, but 21. I have showed the rate of transition, then N2 into rho nu, N2 into rho nu. We can number this as the third equation. So, totally for 3 processes, we have 3 equations. One is the absorption equation, remaining 2 are your emission equations. Clear? Okay. So, the absorption and the emission processes, which is according to Einstein absorption and emission processes are all based on the Planck's law of radiation. Okay. In addition to this, the population of the energy levels obeys the Boltzmann statistics. Okay. Under thermal equilibrium, the population of the lower energy level and the higher energy level are all purely obeys the Maxwell's Boltzmann distribution law. Okay. So, next here we are going to say this as Einstein's theory. Einstein's theory. Einstein's theory. Einstein's, just I am writing another sentence, you can take it as notes. Einstein's theory of absorption and emission, are all based on Planck's theory of radiation. Planck's theory of radiation. And under thermal equilibrium, population of the energy levels obeys Boltzmann distribution law. Okay. Now, we have to consider under thermal equilibrium condition. So, just I am writing under thermal equilibrium. Under thermal equilibrium, we can highlight this. Under thermal equilibrium, rate of absorption which is equal to rate of emission. Okay. So, this is the statement, rate of absorption which is equal to rate of emission. How many processes we have? Totally 3 processes. So, under which only one absorption, whereas 2 emission processes. Okay. Shall I write here? Okay. So, the rate of absorption AB which is equal to, just I am writing this notation alone, rate of absorption RAB which is equal to RSP plus RST. Now, we have the values, clear, isn't it? So, 3 equations, okay. I am going to write it here. What is RAB equation we have deduced here? B12 N1 then rho nu which is equal to, for SP we have derived as A21 into N2 plus RST we have the equation as B12 N2 into rho nu. We have substituted all these processes, 3 processes final equation here. If you see here, we have this energy density terms. I have to rearrange it in one side. So, for that I am bringing this density term to the left hand side of this equation. What about this term 1 to N1 rho nu minus, because we have this side as plus, if it bring it to this side, B21 N2 into rho nu, clear. So, which is equal to A21 into N2. We have just finalized up to some extent, okay. If you see here, this is the common term I am taking outside the bracket and I am writing in the remaining terms inside the bracket, B12 N1 minus B21 into N2 which is equal to A21 into N2. Now, we need this energy density. So, energy density can be keep in the side, the remaining terms to the RHS of the equation. Next, rho density, energy density. This rho nu which is equal to, the numerator we have A21 into N2 by B12 by B21. Then here here I have this as N1 minus B21 into N2, okay. After getting these two terms to that side, we have this equation. Now, I am going to divide the above equation by B21 into N2, that is nothing but our second term, okay. If I do like that, the next equation will be of A21 N2 by B21 into N2 by, the first term will become B12 into N1 by B21 into N2. What happens to the second term? Same, okay, same thing we are going to divide, means it will become 1, okay. So, this is our energy density equation and I can just put on bracket for this N1 and N2. I will tell you why I have just given like this, clear? Think you all get clear about this equation. 3 equations over, this is our fourth equation, okay. The energy density which is equal to this term. Now, and if we can, this can be neglected also. Next one, I am going to substitute one value for this N1 and N2. What is N1 and N2? Number of atoms in the ground state and the excited state. So, for that already we have mentioned here the energy levels obeys Boltzmann statistics. So according to that, by Boltzmann distribution law, N1 can be written as N0 into e to the power of minus E1 by kBT. Okay, I'll explain this. What is N0, kB and T. Okay, I'll write it here. N0 is nothing but number of atoms at absolute 0. Kb, K suffix B is nothing but our Boltzmann constant. What is T? T is nothing but the absolute temperature. You all know absolute temperature. Okay. I think each and every term here, that is exponential of E1 represents the lower energy state or ground state, Kb is the Boltzmann constant, T is the absolute temperature, N0 represents the number of atoms at absolute 0. Okay. So similarly, we can write for N2. Can anyone tell me what is the value of N2? Okay. So good. N2 which is equal to N0 into e to the power of minus E2 by kBT, because this is the constant and here the variable is energy level. Okay. I can write the next equation here as N2 can be written as N0 e to the power of minus E2 by kBT. Therefore, already why we are doing this process? Because we need the value of N1 and N2. Clear? So, I can write the next, therefore, N1 by N2. N1 by N2 which is equal to, just substituting the values of N1 in the numerator as N0 e to the power of minus E1 by kBT divided by N0 e to the power of minus E2 by kBT. What is the next step? Can anyone tell me? So here we have to cancel this N0 and N0. And therefore, the next term N1 by N2 which is equal to, if I bring this term to the numerator, what happens? Exponential to the power of, I can write it as E2 minus E1 by kBT. And in the beginning itself, I have mentioned what is this E2 minus E1. So, since E2 minus E1 which is equal to h nu, therefore, the value of N1 by N2 can be substituted as e to the power of h nu by kBT. Okay. So, now I can write, substitute the value of N1 by N2 in fourth equation. Therefore, rho nu which is equal to A21 by B21 by B12 by B21. Here we have e to the power of h nu by kBT minus 1. Okay. So, here we have shown this E2 minus E1 as h nu. In the beginning itself I told you the energy difference is equal to h nu. So, here e to the power of h nu by kBT minus 1. Okay. So, here we can box this equation. equation number 5. We can take this equation number 5. Here, this equation, or we can write the above equation good agreement with Planck's law of radiation. Therefore, from the Planck's law of radiation, from the Planck's law of radiation, we can write the energy density, as rho nu, which is equal to 8 pi h nu cube by c cube divided by e to the power of h nu by kBT minus 1. Okay. So, you can keep this as equation number 6. So, directly we have introduced this from the Planck's law of radiation. Already we have discussed in the beginning, it obeys the Planck's law of radiation in Boltzmann statistics, as well as it is similar to that of our Planck's law of radiation. So that if you see the energy density, left hand side we have the energy density, right hand side this term from the Planck's law of radiation. If we compare these two equations, we have to compare. We are nearing the solution for the heading. What is the heading here? One is nothing but the relation between spontaneous emission and the stimulated emission. In addition, we have given the Einstein's quantum theory of radiation. So, we are just nearing the final equation. If you compare on comparing equations 5 and 6, we can write. What about the numerator? We have A21 by B21, which is equal to 8 pi h nu cube by c cube. Okay. And what about this denominator? The denominator in the place of B12 by B21, we have 1. Okay. So, if you look into this, I can write this second term as B12 and B2 or B12 which is equal to B21. Okay. Or I can equate this as B also, which is nothing but the constant being introduced during the first process, absorption, which is equal to the stimulated emission. This constant is being introduced during the stimulated emission. So, this B12 which is equal to B21 which is equal to capital B. And if you come on to this, here this constant A21 which is being introduced during the spontaneous emission. Here this is during the stimulated emission. According to this equation, if you see this frequency, that is spontaneous emission, is equal to the frequency of the incident radiation. Clear? So, and in addition to this, in order to achieve the stimulated emission, because we have discussed During the stimulated emission only, photons, more photons are being emitted with energy, same energy, phase difference as well as coherent in nature. So, that is the key factor for our laser action we have discussed, isn't it? So, in order to achieve that population inversion, we need certain techniques. That is, population inversion means, you know very well, that is number of atoms in the excited state must be greater than the number of atoms in the ground state, that is N2 must be greater than N1. To achieve that population inversion, various techniques, pumping techniques is being, artificial methods, pumping techniques will be introduced. Okay, that and all we see in the next session. So, before that, if I put A21 which is equal to A, therefore, here there are two constants being introduced, capital A and B. So, what are this capital A and B? Capital A and B are called Einstein's coefficients. Einstein's coefficients. It gives the probability of spontaneous and stimulated emissions, spontaneous and stimulated emissions. Okay. So, here you see principle of spontaneous emission and stimulated emission. So, how this process is being based on that we have the explanation, and we have finally reached the quantum theory of radiation. There we have introduced two constants. From that two constants we have discussed all these probability functions, that is spontaneous and the stimulated emission. Clear? So, the remaining topics, which is the population inversion, what about the different methods of pumping techniques, in addition what is active medium, active center, what are all the components of laser. So, that kind of things we will discuss in the next session. Okay. So, thank you all, thank you very much. So, next we will see, already I told you what is mean by population inversion, just I will tell you. Population inversion. So, for this also you need to consider two energy states E1 and E2, and here just I am showing the number of atoms. Okay. So, this is nothing but the higher energy state, or we can say it as the excited state, and this is our ground state. Okay. So, if you see this, the number of here also we can mention it as N1 and N2. So, N1 is nothing but number of atoms in the excited, N1 is the number of atoms in the ground state, whereas N2 is nothing but the number of atoms in the excited state. So, after seeing this picture or the diagram, you will be able to give the information. Number of atoms in the excited state is higher than the number of atoms in the ground state. So, if it looks like this, that is N2 is very greater than N1. Okay. So, by using this very simple equation, you can define what, if it is asked in the part A, what is mean by population inversion. Okay. So, if it is like this, we can write the definition as, just I am giving only the hint, number of atoms in the excited state is greater than the number of atoms in the ground state. Okay. Okay, so you'll ask me how to reach this inversion process, which means usually all the atoms are in the ground state, but we are just making the atoms as excited one, and for this process we have to depend on an artificial method. So, that artificial method of exciting the atoms from the ground state to the excited state, which is called as the pumping. Okay. So, pumping, I will give the definition here. Pumping, artificial method of making the atoms as excited one. Okay. So, that is an artificial method. So, there are different methods. Okay. So, we have to concentrate on this word, artificial method of exciting the atoms from the ground state to the excited state, that is called as the pumping. There are different methods are available. So, here I will give you the methods. Optical pumping, second one is electric discharge pumping, third one is inelastic atom collision pumping, and fourth one direct conversion pumping. Once again, I will read these topics: optical pumping, electric discharge pumping, inelastic atom collision pumping, and direct conversion pumping. So, these are all the easily available pumping techniques to achieve the population inversion. Okay. If you see here, different types of lasers are also available. One is the solid state laser, gas laser, liquid laser. So, different types of lasers are also available. And if you see for a solid state laser, the best example is ruby laser and NdArc laser. And if you go for the gas laser, carbon dioxide laser, CO2 laser are available. And if you go for the new topic, that is semiconductor laser, for semiconductor laser we have the homo junction and heterojunction semiconductor lasers are also available. And if you see in the case of semiconductor laser, we are going to use the direct band gap semiconductors. So if you see the difference, what is mean by here types of lasers. First one is solid state laser. For solid state laser, if you see the example ND-YAG laser. So this ND stands for neodymium yttrium aluminum garnet. Okay. So ND-YAG laser stands for neodymium yttrium aluminum garnet laser. And next example, the known example, that is nothing but our ruby laser. Okay. So these are all the examples for the solid state laser. Next, if you go for the gas laser, in the case of gas laser, you might have heard about, the best example is helium neon laser. Helium neon laser. And second one is CO2 laser. CO2 laser, it is a molecular gas laser. I have just given the example. And then third category, third important type of laser is nothing but our semiconductor laser. Okay, semiconductor laser. In the case of semiconductor laser, example we have homo junction and hetero junction laser. If you go for this semiconductor laser, we have to depend on the direct band gap semiconductors. Think you know the example. If anyone asks you about what is give some example for semiconductor means, all of you suddenly will explain or you have given the example as silicon and germanium. Okay, but they are all indirect band gap semiconductors. Here we are to discuss about direct band gap semiconductors. So what is the difference between the direct band gap and indirect band gap semiconductors means? In the case of direct band gap semiconductors, here it emits the photons. The output will be of photons. That is, during the recombination process, the emission in terms of photons. Okay, you can ask me what is the example for this semiconductor laser means? The best direct band gap semiconductors are the examples. Here I can give it as gallium arsenide, indium phosphide. So these are all the direct band gap semiconductors that can be make into this homo junction and heterojunction in terms of their construction process. Okay. So here we are going to have a single junction which is going to be made with the help of these materials, gallium arsenide or with the help of indium phosphide. Okay. So here heterojunction means different layers are being made with this heterojunction in the case of our heterojunction laser. Clear? So in the case of, already I told you, in the case of indirect band gap semiconductors during the recombination process, in the case of germanium or silicon, heat energy is being given. Okay, that is during the recombination process it will emit the heat as the output. But the speciality of this direct band gap semiconductors is nothing but during the recombination process it emits the photons. Okay. So, these are all the types of lasers: solid state laser, gas laser and semiconductor laser. Okay, thank you all.